Welcome PCS members and friends to our PCS IBS seminar. Today we are very happy to host for the second time this week Professor Chen Jing-Yuan from Institute for Advanced Study, Tsinghua University, Beijing, China. And today we will hear about how to find the Mies topological operators in lattice theories. Let us welcome our speaker.
Thank you for the introduction, and I'm very grateful for having a second opportunity to talk about something totally different here. As we know, in the course of development of theoretical physics, the cross-fertilization between condensed matter physics and high-energy physics has been tremendously important for some of the most important breakthroughs in history, such as the relation between Anderson's theory of superconductivity and the Higgs mechanism in particle physics, as well as some Feynman's works, Landau's works, Xianyang's work, and so on. So this talk is a talk that is not limited to the field of condensed matter or high-energy physics. Rather, what I will tell you about is how to take some key inspirations from some previous developments in condensed matter physics, as well as from high-energy physics, and solve some generally important problem in both high-energy physics and condensed matter physics. Okay? So let's organize the talk like this, where I will begin with Wilson's dream of relating continuum quantum field theory and lattice quantum field theory, and what the problem in mind is. So as we know, Wilson has also made tremendous impact in both high-energy physics and condensed matter physics. So one of this dream of his is related to both areas. So the general question, to put in a very broad scope, is quantum field theory today is very much like calculus in the 1700s, where the calculus back then, developed by Newton, was able to describe the physical world, but mathematically we don't exactly know what dx means, right? Like it can describe the physics, but we don't know exactly what we are talking about. And well, later, we know in the 1800s, there is this, all of us has taken some analysis, I think, in undergrad, where there's this delta epsilon language developed by Cauchy and others that finally made sense of dx so that a calculus becomes well-defined. So the quantum field theory today is similar. A lot of times we know how to use a quantum field theory or statistical mechanics, where we have a partition function or path integral. We integrate over some exponentiation of Lagrangian or Hamiltonian in statistical mechanics. But the problem is that if the space-time is a continuum, then the path integral or the configuration space to be integrated over is infinite dimensional. And we don't really know what it means to perform this infinite dimensional integral. This is not limited to high energy or condensed matter, this problem. However, in condensed matter, we usually have a lattice, right? When we have a lattice, the infinite dimensional integral in the continuum becomes finite dimensional. So that inspired Wilson that we should think about quantum field theory on a lattice in general. So of course, Wilson was deeply influenced by the lattice theory, the actual lattice theories in condensed matter, but he wants to take the idea that in general, because we are able to define the path integral or the statistical mechanics or the lattice, so maybe even for continuum problems, we want to put the problem on a lattice to define the path integral, right? This is a very straightforward idea. And once you put the continuum path integral onto the lattice, the infinite dimensional integral becomes a finite dimensional if the system size is finite. And of course, the derivative, if you take the rough idea from calculus, will become the difference between the neighboring lattice size. Those are all very straightforward ideas. And Wilson used this to make progress in some very important fields in high-energy physics, inspired by the idea in condensed matter physics. And one of the most important aspects is now that the computer can understand what this infinite dimensional integral, which becomes finite dimensional, means. Now the computer can understand that it can perform the Monte-Carlo calculation in both condensed matter and high energy. For example, in high energy physics, an important field is a lattice QCD, where you put the Yang-Mills theory and quarks on the lattice to simulate the QCD.
So who come up with the lattice interpretation first, Carnot or Wilson?
Wilson came up with the lattice gauge theory first. Yeah, and Wilson was also the person who promoted to use the lattice theory to do Monte-Carlo calculation, even in high energy physics. Yeah. So this is really bridging these two fields, and there's a big community in lattice QCD in the world. Some people spend their entire life doing these things. So the lattice QFT is very good because we can understand what it means, and we can also do Monte-Carlo with it. But there's an ultimate problem with lattice QFT in general. It's okay, we put on the lattice, it looks like if we make the lattice small enough, it should have some approximation to the continuum. But whether the continuum exists, it's hard to prove mathematically. And actually, this is related to one of the holy grail of mathematics, where you might have heard that there are like 7 major mathematical problems of the millennium price problem. And one of those is to define the Yang-Mills theory. And one approach to define the Yang-Mills theory is to define on a lattice and show that it has a convergence into the continuum, but it has not been proven. But numerically, we can check whether it looks like it converges, right? So, but anyways, there's an ultimate problem of a lattice QFT. It's relation to continuum QFT. Of course, I'm not going to discuss about solving the millennium price problem, and I cannot solve it. But there's a more immediate problem, which shows that even if we don't care about this ultimate problem for now, there's some immediate problem we have to solve. After solving this immediate problem, maybe we can be more ambitious. But now we need to solve the immediate problem first. That is, the topological operators are lost in the lattice quantum field theory, are in generally lost. And one important example in lattice QCD is the instanton in lattice QCD, which was a famous long-standing problem for more than 40 years since Wilson's invention of lattice QCD. And there are also many examples in strongly coupled condensed matter problems. Some of those are resolved, some of those unresolved, and I'll discuss why there's such a problem in the next few slides. So in this talk, I will talk about how to systematically solve this intermediate problem. Now, this immediate problem. Solving this immediate problem makes this topological operator becomes well-defined on the lattice so that we can compute their correlations in Monte-Carlo and also understand some formal problems better in both condensed matter and high energy. And then maybe in the future, we can use the idea here to help us understand it more.
Can you explain what you mean by the topology?
I'll explain that in the next few slides. Yeah.
So, sorry, before you continue, I think I missed this information. So what was exactly Wilson's dream on this topic?
Okay, Wilson's dream is to make the quantum field theory well-defined to such an extent that the computer can understand it and do calculations. Because usually when we do QFT in the continuum, there are a lot of tricks and approximations and this and that. We do that by experience, but we don't really know why we are doing that. Then the computer certainly cannot do that. So you need to make the quantum field theory well-defined so that the computer can understand that and do calculations. Yeah, that's one way to put it. But of course, ultimately, it's not about whether the computer understands, it's whether we understand it well enough to work with it. Yes.
So to understand for computer, but not for us.
Also for us.
Also, why?
We don't understand
computer is computer. Where are we? So it's different vision.
Yes, but when we do those continuum calculation in quantum field theory, there are a lot of unjustified procedures. And there are also a lot of non-perturbative effects. A lot of those come from topological operators.
But you mean that understand it means to make some calculation. I think that understand means something different. Understand. I don't, of course, don't pay attention.
Well, being able to do general calculations is part of understanding. I guess at least we agree on that. Yeah. But if you put on the lattice, then the theory is completely well defined, right? There's no ambiguity.
Even if we have infinite word,
Infinite what? Infinite size?
Infinite dimensions or lattice. What is the number size of your lattice?
Yeah, if it's big enough, then the problem is whether it converges. But if we don't care about convergence, then at least we know what we are defining on the lattice, right? Yeah. Whether when you make the lattice smaller and smaller, whether it converges is another problem. But at least for a given lattice,
Smaller in comparison with lattice, step on lattice.
yeah, for example, with the energy scale you care about, you are interested in. Yeah.
In the lattice, you think about the periodic boundary condition.
For example, you can do that, or you can also consider open boundaries in general. But in practice, a lot of times we will consider periodic.
Depending on the type of lattice, you can construct a lot of type of boundary condition.
Yeah. So yeah, that's also that's part of the information in lattice theory. Yes. Right. So in this talk, I will talk about how to systematically solve this immediate problem. Now, of course, I haven't told you what topological operators are in general, but to give you some sense, for example, in the XY model, which will be one of the important examples I will talk about soon, like the winding number or the vortex will be a topological operator, or the skyrmions in general, or Dirac quantized flux, monopoles, those kind of things. Yeah, I guess that sort of answers it. Yeah, but these operators are in general lost when you put on the lattice. And in some cases, we know how to retrieve them, but in general cases, we don't. And that's why I want to solve this problem. Okay, okay, this is the slide. So there are the many topological operators, especially the ones that are going to be lost are the ones that come from continuous valued fields. So what are some examples? So one is the familiar XY model in condensed matter physics, where you have a degree of freedom is lives on a circle. S1 means a circle, one-dimensional sphere is a circle. And then it's an XY model, the topological operator is a winding number in 1D or vortices in higher dimensions, right? And then similarly for U1 gauge theory, where again you have a circle, but the circle is not the degree of freedom itself, it's the gauge redundancy is the circle. You have a Dirac quantized flux and monopole, and also abelian Chen-Simons and abelian instanton, these kind of things. And of course, this is very relevant to, for example, fractional quantum Hall, etc. And then there are other examples. This is a two-dimensional sphere, which is like a sphere living in 3 dimensions, our familiar sphere. Right, like the direction of the spin, for example. The direction of the spin lives on a sphere. And then there are the non-linear model is also appear very commonly in condensed matter physics, right? The direction of the spin. Then the topological things involve the Barry phase. The Barry phase is topological because the total Barry phase around the sphere is 2 pi, it's not 0, right? So the Barry phase is topological. And if you are in 2D, there is a skyrmion number, and if you are in 3D, there can be a hedgehog configuration. Maybe I can draw a hedgehog configuration. Like if you are in 3D, you have a cube, and then the spins are all sticking out in the outwards directions. I guess you know what I'm trying to draw. Something like that. And then further away from the cube, they are all sticking out, looks like a hedgehog. This is a hedgehog configuration. Those are the topological configuration for the direction of the spin on a sphere. And then we can also consider 3-dimensional sphere. A 3-dimensional sphere does not describe the physical spin, but in some strongly coupled condensed matter model like the deconfined quantum criticality and so on, maybe the extra spin and some other degree of freedom form some emergent 3-dimensional sphere. So that appears in some strongly correlated condensed matter systems, at least in theoretical proposals. And also in high energy physics, there's a very physical example, that is the pions. Even if we do condensed matter physics, we probably know that there are 3 kinds of pions, and the 3 pions actually parameterize 3-dimensional sphere in the nuclear physics. And then there are Wess-Zumino-Witten terms that is an analog of Berry phase. And also there is a three-dimensional skyrmion. And for the example of pions, the skyrmion is actually something we are very familiar with. The skyrmion in the pion anisotropy model in reality is just the protons and neutrons. Okay, so the protons and neutrons can be viewed as a topological operator in the pion theory. And actually that's Skyrm's very first example of skyrmion. Maybe in condensed matter physics, we are more familiar with this skyrmion, but Skyrm's first example of skyrmion is actually the proton and neutrons in the pion theory. And again, in 4 dimensions, there can be hedgehogs, which corresponds to the neutrons and proton number being non-conserved. And then you probably want to prohibit it because the neutron and proton numbers are conserved. And finally, there is a SUN gauge theory, like in the QCD of nuclear physics. So in 3 dimensions, there can be Chen-Simons, and in 4 dimensions, there are instantons, which are very relevant to a lot of phenomena in nuclear physics. And then in 5 dimensions, there's Young monopole, which is an analog of the Dirac monopole, all those kind of things. So we can see in all these examples, there are very physically relevant examples in both condensed matter and high energy physics. And these examples have a different topological characterizations. These examples where the space is a circle, the topology comes from pi1. What does pi1 mean? It means how many times the winding number of a circle around another circle. Okay, like if we have a loop of a string or rope, then we can wind it around another circle arbitrarily many times, right? But the number of times is an integer, right? So it's some integer winding number of a circle around another circle. That's comes from the pi1. So all this topological physics comes from this pi1, which is a 1-dimensional winding number. And the topological physics here comes from pi2, which is how you wrap a 2-dimensional sphere around another 2-dimensional sphere. That can also be an integer winding number. And this comes from a pi3, the winding of a 3-dimensional sphere around another space, like a 3-dimensional sphere or so on. These are the topological physics that comes from this winding number. Okay. So these are all very physically relevant examples, and they have different topological characterizations of 1-dimensional winding number, 2-dimensional winding number, 3-dimensional winding. Right. So these are all examples of topological operators, and these topological operators will be lost if you put the continuous valued field theory on the lattice in the traditional way. And we will see with the simplest example why this is happening.
So, sorry, in case of XY model, we can define the number of, like, we can calculate the number of vortices and anti-vortices on a lattice, right? By just summing the theta.
Yeah, I'm going to explain that in the next slide.
Okay.
Yeah. Okay, yeah, not in the next slide. Let me finish this part. Okay. It turns out that the simplest, some of the simpler cases like the pi1 physics and pi2 physics has been solved. This has been solved by villainization, which was actually not invented by Villain, but invented by BKT, especially by Berezynski. And it's obvious why they invented this method, because they want to talk about the vortex to derive the BKT transition. So it's a very important development in theoretical physics. And the second problem is also solved by the spin non-decomposition, which is also very commonly used in strongly coupled condensed matter systems. But the more general cases are unresolved. And they are unresolved not because they are unimportant. These are very important problems. And also not because people are too lazy. People work very hard on these problems. But why are they unresolved? It turns out that it's because the sort of the vague ideas that people use to develop these methods does not work anymore. To work out these cases, it turns out you have to think more systematically about what is the most fundamental thing behind the previous ideas. And if you extract the most fundamental things and in a systematic way, you can solve this problem. But just the usual trial and error idea doesn't help with these problems. I'll explain why. Okay, but the general idea is what becomes wrong in this naive picture of lattice theory is that Indeed, you want the path integral to become finite dimensional, but not in this naive way. In particular, you don't just simply replace the derivative by a difference. Okay, that seems to be the natural thing to do in calculus, but this is not capturing the full information. So we need to do some conceptual level refinement of what we mean by lattice field theory. Okay, so let's start with the known example, the villainization for the XY model, and also I'll briefly mention the spin-on decomposition for the direction of spin-on spin. Okay, let's consider XY model where you have a spin that takes value in a one-dimensional sphere or one-dimensional circle. And for simplicity, let's look at a one-dimensional lattice as well. So this is a lattice with 6 lattice sides. And then each lattice side has a direction of spin that lives on a circle. Okay. Then looking at these two pictures, we feel this has winding number 1 and that has winding number 0, right? That's our feeling. But we also can sense that there is some problem. Why is there some problem? Because we can continuously deform one configuration to another configuration. And this is only possible on the lattice, but not in continuum. How do we do that? Because the lattice is made of the degrees of freedom on individual lattice sides, right? We can just gradually turn this direction to become this direction, and gradually turn that direction to that direction, right? So we can, by gradually turning each of the direction of each of the spins, we can continuously deform this configuration to this configuration. But then you'll say, okay, then when does the winding number change? Right? Because if something is topological, then we don't expect it to change if we do continuous deformation.
You do local transformation between these two.
Right. Or I can also simultaneously turn all of these at different speeds so that they end up at here, right? As long as you can turn it individually, one by one, then you can also simultaneously turn them and go from here to here. Yes. But that seems to contradict with the idea that the winding number is topological, right? If something is topological, then you don't expect it to be able to jump if you continuously change your field configuration. Okay?
Sorry. You did not think about the translation.
Translation? Translation symmetry? The theory is translationally symmetric around the circle.
You think about the direction. Yeah, translation. It's not. It's broken the translation.
Why? This is one configuration.
Angry. You think about the arrow.
Yeah, yes.
What is broken the
theory is translational invariant around the lattice and also rotational invariant around each spin. But these are two particular configurations in the statistical mechanics or in the path integral. These are two configurations. But then you need to, in the statistical mechanics, you need to sample all possible configurations. Yeah.
So one gives the difference of continuum model and lattice model is translation.
Oh yeah. Lattice model does not have continuous translation symmetry, but it has the lattice translational symmetry. Yeah. But it's independent from this problem I have. Yeah. So it's not related to whether you have continuous translation symmetry or lattice translation symmetry. It's just if something is topological, then you expect it not to jump when you continuously deform the configuration.
So in the large n limit, but it's still finite, you can still deform one to each other. That's what
Yeah. No matter how many lattice sides, right?
Okay.
Yeah. But of course, you can say, okay, maybe if you consider the energy, when two of these spins have a very different angle, the energy is very high. But even if the energy is very high, that means the statistical weight is very small, but it can still happen, right? The statistical probability is non-zero. It can still happen. Then you don't know when the W change discontinuously. Yeah. So we can think of this as a more mathematically, that is, if we consider the total configuration space on the lattice, right? Okay, what is the total configuration space? The configuration space on each lattice vertex is a one-dimensional circle, right? So the total configuration space on the lattice is just a one-dimensional circle to the power of the number of vertices. That means just there are many copies of the circle, right? And then if we want to assign a winding number, it's like we want to assign an integer to this configuration space, yes? But this configuration space is a connected space because a circle has only one connected component, right? A circle is connected. So many copies of a circle is still connected, has only one component, right? So it's impossible to map a connected space to a discrete number. If you either the result is either single value if you want to map to be continuous, right? Because you can go from any configuration to any other configuration continuously. If you want to map to be continuous, you always map to a single value. But then it's very unphysical because for this we are feeling there should be different winding numbers. And it's almost unethical because if it's single value, if you say these two have the same winding number, you're lying to yourself, which is not very ethical, or you're also lying to others. Or another possibility is you allow this map to be discontinuous. You can say, okay, maybe this configuration can be continuously deformed to that configuration, but at the middle, I would just let W jump by 1. But then in that case, it's discontinuous, right? So it's also not very satisfactory and will actually cause some practical problem. And now by looking at this example, we can recognize that this problem is actually the same for any continuous valued field once you define it on lattice, right? It does not rely on whether I have a circle or whatever other continuous value space, and whether they live on the lattice vertex or the lattice link or whatever, right? As long as you have a continuous value space that is connected and you put it on the lattice, no matter it's on the vertices, on the link, or on where, you always encounter the same problem.
So what happens if your configuration space is also quantized, like depending on the system size? It can take only those values according to the system size. Like the momenta, if you have a 1D chain, so the finite number of lattice side, then it has only certain discrete momenta.
Yes.
So in that case, also this problem.
But this lives on a circle. The circle is continuous. If you look at the real space, the value in the circle is continuous.
Yeah, circle is continuous, but if you fix the number of points on the circle.
Yeah, I fixed 6 points on the circle.
Yeah, so if you also fix that accordingly, the theta also take the specific values.
Oh, you mean the angle also becomes discrete?
Yes.
Yeah, but then there will be no winding number, no well-defined winding number. And you lost a lot of interesting things such as a vorticity and so on. And you don't get the BKT transition, for example. You get some other phase transition, but not the BKT transition in 2D or the spontaneous symmetry rating in higher dimension.
Well, on 4 sides you have 90, 90, 90.
Yeah.
So you still get 2 pi. So
yes, but the transition will be of a different character when the degree of freedom is continuous versus discrete. Right.
So our question is, do I understand correctly that if you, instead of fixing 6 lattice sides, if you have a continuous S1, let's say, and these spins can be anywhere on S1.
Right.
In that case, what is the configuration space?
Right. In that case, the configuration space has this connected component of different winding numbers. The difference is when the space is not a lattice but a continuum, then there is indeed spin on every point. Then you cannot turn each individual one because you need the spin to vary smoothly when you smoothly move along the circle.
No, but
the direction of spin also.
Mathematically, what is it? I cannot think of it like S1 to the power of infinity.
Right.
What is it really?
The configuration space will be but it will be hard to describe, but the configuration space will be disconnected and will be classified by the winding number, which is exactly this number, right? So somehow on the lattice, we will see the intuition behind the difference very soon, yeah. But on the lattice, we see that there is a problem, and this problem is not limited to this model, it's very general. And anytime you have a continuous valued degree of freedom on the lattice, you encounter this problem. Yeah. Okay, so the V-line model, roughly speaking, take the following idea. We say this configuration has winding number 1 and this configuration has winding number 0. What we really mean, let's say this, what we really mean is with a high probability, the winding number is 1 in this configuration. But the winding number can also be other values in this configuration with lower probability. Also, for this configuration, the winding number has high probability to be 0, but it can also be other values with lower probabilities. But then what determines the probability? How to assign the probability? Okay, so that's the real key idea of the V-line model that is behind Berezynski's BKT transition work. Let's think about the following. Let's think about the lattice as being embedded in the continuum. That is, we think about the lattice as sampling some points in a continuum circle. Okay, so we are sampling 6 points on a continuum circle. In that case, we can ask the following question. The lattice link then would correspond to a segment on the continuum circle, right? Then we can say, how does this theta interpolate to this theta if it really is in the continuum, right? If we think of the lattice as embedded in the continuum, we can ask, when at this sampling point, we have this theta, at this sampling point, we have this theta, but across the lattice link, we are actually going through a segment in the continuum. How does the theta gradually change from this value to that value, right? It's a very natural idea. And then with this idea, we come up with this picture. Let's say this theta is at this point on the circle, right? And that theta is at this point on the circle. Then, of course, the interpolation looks like it will interpolate this way, right? But it's also possible, because we haven't sampled the points in the middle, it's also possible that it interpolates the other way around, right? Or it can even interpolate with multiple rotations until getting here. All those are possibilities. But it's intuitive to think this way of interpolation should have the highest probability. And that way of interpolation should have a lower probability. And if we go around a few times until getting here, then those should have very low probability, right? Especially when the lattice size is very small. So, but allowing the possibility is important, even though the probability is low. Okay, so, or we can say the gamma, we can find a real value gamma, which is the integral of d theta from the vertex v to the vertex v prime, okay? So, right. So if we define gamma in this way, which is the total distance that it has traveled along the interpolation, then we know the mod 2 pi part of gamma, or e to the I gamma, needs to be e to the I d theta, right? However, the integer part of gamma is not fixed because it can go this way, that way, or go around a few times. So gamma is a real number such that the U1 part is fixed by the difference between the two thetas, but the integer part is not fixed, okay? So we need to sum over the integer part with different probabilities. And the different probabilities, like this gamma has the highest probability, that gamma has lower probability, and a few winding should have even lower probability. That kind of assignment, right? So we should introduce a new degree of freedom, which I call M, which is the integer part of gamma, to be summed over in the statistical mechanics or in the path integral. So in terms of the lattice weight, it's look like this. The XY model has a weight. It has a weight that in terms of cosine of the difference of theta. Why you need a cosine? Because the theta is only well-defined mod 2 pi, right? So you need some periodic function, for example, cosine. Then on each lattice link, you have such a weight. So it's the horizontal axis is the difference in theta, and it's a periodic with periodic 2 pi, right? So the lattice weight in the XY model should be a periodic function like this. And in the Relay model, what we do is we separate this periodic function into a sum of many terms. Each term has only one peak, and that is to sum over the integer m in the gamma. Right, in the previous slide, we said, okay, actually also in this slide, gamma, the U1 part of gamma is fixed, but the integer part of gamma is not fixed. So we need to sum over all the possible integer parts. After summing over all the possible integer parts, we will recover that picture. But now, before summing over the integer part, we have just individual peaks.
Excuse me, this is same as the is the boundary.
The TC. If the boundary dependent, the TC will slightly depend on boundary condition, but if your system size is large.
This tree is same as looks like the.
Oh, you mean these two models? Is the TC the same? Right. So I use some approximate sign here because you don't have to have them exactly the same to produce the same universal physics. But if they are slightly different, then the TC can be slightly different. But given any weight that looks something like this, any periodic weight that looks like this, you can always choose some peak that approximate this to arbitrary precision as you want. So the TC can be arbitrarily close to each other, right? But a lot of the times you don't need to exactly have them equal. You can have some difference that is non-universal, then the TC will be slightly different. Yes, but the universal physics such as the BKT transition and so on are unaffected. Right. So this is what the Relay model is. So yes.
So what was W again?
The weight on a lattice link. The path integral weight
So
e to the power of. For example, we can say Wxy is equal to, on each link is equal to e to the 1 over temperature, 1 minus cosine of the difference of theta. That kind of thing. On each link. Then we need to product over all the links because each link has the weight. This is on a certain link L. Yeah. So we need to product over all the links. So this is the total path integral weight. Yeah. But it doesn't have to be exactly this. Just anything that looks like this have the same universal physics, right? And right. So with the Relay model, we can define an ambiguous winding number. Why is that? Because gamma keeps the information of how this value is interpolated to that value, right? And moreover, we know that the shortest interpolation have the highest weight, right? So with highest weight, gamma will be equal to 2 pi over 6 here, and 2 pi over 6 here, 2 pi over 6 at all the links. Then with highest weight, the winding number will be the gamma over 2 pi sum over all the links. Yeah.
Somehow this weight information is hidden in the XY model itself.
Right, this is a good question. We can view the XY model as the Relay model with the integer summed over already. So the Relay model is a refinement, it's like a refined version of the XY model. But the XY model has the same physics as the Relay model because it's just the Relay model summing over some degree of freedom. But if you want to do some observation that is expressed in terms of this degree of freedom, then you shouldn't sum over it first. Right.
I guess a related question would be that if I am working with the XY model,
yes,
where I'm working on a continuum,
yes,
then as you explained before, it was difficult to describe the configuration space.
Especially on the lattice, it's not well defined.
Let's say I'm working on continuum.
Okay.
So continuum makes
right. Then you don't exactly know what the path integral means.
Yeah. So then my question is how? So you are saying that you have this homotopic group. Because when I have, when I have this integer number of something, then it must be a homotopic group of something. So what is that something?
It's the homotopic group of how the one-dimensional space-time winds around the target space of the direction of spin.
one-dimensional
space-time winding around the direction of the spin, which is also a circle.
Okay,
Yeah,
so that space is
S1.
R2 cross S1?
S the one-dimensional space-time or loop is an S1,
Okay,
and the one-dimensional direction of the spin is also S1.
so it's a torus.
Yeah, so no. It's a map from an S1 because it's e to the I theta x, where x also lives on a circle, right? And this also lives on a circle. So this is a map from a circle where x belongs to another circle where e to the I theta belongs.
Okay,
So it's a map from a circle to a circle. So that has a winding number.
so that's the configuration space that you were talking about.
That's a topological part of the configuration space. Yeah, this is the configuration space. And the winding number is the topological information in the configuration space. Yeah.
So if I have to look at the winding number, then I'll have to know the homotopy group of that e to the I theta x.
Right. You're right. So the problem we want to do now is we want to be able to describe this on the lattice. Right. And the way to do that on the lattice is instead of between two lattice vertices, instead of looking at just e to the I d theta, we look at this gamma, such that gamma is a real number instead of an U1 angle, such that the U1 part of gamma is fixed by this, but there is also an integer part of the gamma. With this, because gamma literally captures how the interpolation happens in the continuum, then the winding number will just be the sum over gamma of all the links on the loop divided by 2 pi, which because the d theta will cancel out, right? Because this part will cancel out when you add up the gamma on neighboring links. So the final result will just be a sum over the integer m. So this is manifestly an integer, right? That's why if you start with the xy model, which is the V-line model with the m summed over, then it will be hard to define the vortex because the vortex is described in terms of m. Right, so you shouldn't sum over m first if you want to describe the vortex, right? Or the winding number. So this is a one-dimensional winding number, but if we are in two-dimensional lattice, the winding number around the plaquette will become a vortex. Right, so in summary, how did villainization capture topology? It's by introducing the extra degree of freedom on the lattice, which is the integer part of this gamma, which we call m, and recovering the information of how fields interpolate from one point to another point in the continuum. Right, it's very intuitive idea, right? Very intuitive idea. And this method is invented in particular by Berezynski, and of course it's so that once the vortex become well defined, then you can derive things about the vortex, such as the BKT transition in 2D or the spontaneous symmetry breaking transition in higher dimensions. And this method is also important for a lot of things such as the boson-vortex duality and so on, which are all very important in condensed metaphysics, and also some anomalies, which I'm not going to talk about. But the idea, I think, is very intuitive. You just introduce the information of how it actually interpolated. Let me just briefly mention that there is some application to lattice gauge theory as well, where in the XY model, you have this U1 field on the vertex. And in gauge theory, because the gauge theory talks about how, like a gauge theory is like when you move from one point to another point, how many phase you accumulate, right? How much phase you accumulate. So the U1 gauge field should live on the lattice link instead of the lattice vertex. Okay, so now the U1 field, the direction of spin, the U1 field on the vertex becomes a U1 gauge field on the link. And this real field on the link, what I called gamma just now, should become some real gauge flux on the plaquette, right? So everything becomes one dimension higher. And the idea is the following. By going around the plaquette, you know the magnetic flux around the plaquette, right? And the magnetic flux is only well-defined mod 2 pi. That's why that's analogous to e to the I d theta before. Now the magnetic flux around the plaquette is well-defined mod 2 pi. However, we can make this a real number if we think about how, if we start with a small circular loop, the magnetic flux is zero. How does the zero magnetic flux gradually increase as we increase the size of the circle until it reaches the size of the plaquette? Then we know the interpolation of the flux. How does the flux interpolate from zero to some value, right? We don't just know it's this value, but we also know whether it interpolated this way or interpolated the other way, right? So that you can apply the same idea to gauge theory. And then the winding number in one dimension becomes the Dirac quantization of flux in 2 dimensions, and the vortex in 2 dimensions will become monopoles in 3 dimensions. And then with this, you can do a lot of interesting things such as Chen-Simons and so on. And there are many more examples of bilinizations, but the idea is similar. I also want to briefly mention the S2 non-linear model. Now the spin no longer takes value on a circle. The spin takes value on a sphere. It's like a spin in the 3-dimensional space. So it takes value on a sphere. Now you want to define the theory on the lattice, then for the same reason as before, the topological configuration, such as this hedgehog configuration, will be lost, right? And how to retrieve this information? And the idea is that on a lattice link, you introduce a SU2 rotation matrix, such that the spin 1 representation of this rotation matrix will rotate you from the direction on one vertex to another vertex. For example, like on one vertex, you have this angle of the spin, and for the neighboring vertex, you have this angle of the spin. Then on the lattice link, you introduce a rotation. You introduce an SU2 rotation subjected to this constraint. Okay, so we can ask, what are the SU2 rotations that are subjected to this constraint? It turns out that you can rotate it like this, right? But there are also other rotations. For example, you can rotate it like this, or rotate it like this, right? Each depth line is a possible rotation. As long as you can rotate this direction to this direction, the rotational axis does not have to be fixed, right? There are many possible rotations. And you can note that the rotational axis just lie around a circle. Can you sort of see that? Any rotational axis that is pointing around the circle about which n and n prime are symmetric is a legitimate rotational axis, such that you can rotate from n to n prime, right? So it turns out that all the possible rotations that can rotate from n to n prime has a U1 degree of freedom, right? Because the rotational angle can, the rotational axis can live anywhere on a big circle about which n and n prime are symmetric. Then it turns out that we have a U1 that parameterizes the rotational axis. And then it's the U1, because the rotational matrix lives on the link, so the U1 lives on a link. And it's actually, I'm not going into details, but it's actually going to be interpreted as the Berry connection in the lattice. So we are familiar with the Berry connection in the continuum, right? And it turns out that this U1 corresponds to the Berry connection on the lattice. So it lives on a lattice link because it's a connection. And right, and then the Berry connection on the link is also like a U1 gauge field, because a Berry connection is just a gauge field. Then we can do the villainized U1 gauge field, and then we can get the Skyrmio number and the hedgehog number without going into details, but that's the rough idea. And the relation between this and the continuum picture is that in the continuum, if we think of the lattice link as a path in the continuum, then you will consider general interpolation from n to n prime, such as this red curve, right? A general interpolation in the continuum from n to n prime will be this red curve. But it turns out it's sufficient to consider only the rotational paths, such as this black curve or the dashed black curves. It turns out we don't need to care too much about the details of how the interpolation happens. We only need to consider a certain kind of path, interpolation path, such as the rotational path. And we'll explain why mathematically. But that's what people do a lot in condensed matter physics. It's called the spin non-decomposition, which is one example of parton construction. So summarizing this known example, we can see the idea is that we have some traditional fields, like the XY model field or the direction of the spin. But we also need to introduce some new fields, such as the integer part of gamma in the V-line model, or like this U1 Berry connection field, etc. We also need to introduce some new fields. And in particular, some part of the new fields is discrete. The thing that comes from the villainization step is discrete. Moreover, the new fields and the traditional fields need to have some suitable coupling in the lattice model. The coupling means the path integral weight or the statistical mechanical weight is a joint weight. Then the discrete part of the new field will determine the topological number. For example, in the V-line model, we said that the winding number is the sum over all the links of the m on the link, which is an integer, right? So the discrete part of the new field will determine the topological number, which means the traditional field will only determine the topological number probabilistically, because the traditional fields and the new fields are related to each other by the probability in the statistical mechanics or in the path integral. Okay. So, and the principle of what the new fields we want, what do we want new fields to do, and what are the requirements in the coupling, is that the new fields and the old fields together should form something that can recover some interpolation information in the continuum, right? Yes.
So can one generalize this, or like including both of the things, like the S1 and S2, or pi1 and pi2?
Yes, you can also consider both pi's at the same time. But for simplicity, I'm only considering one pi for now. Yes. But the general idea is this, right? You have the traditional field, but you also need some new fields with suitable coupling. The new fields and the coupling should be designed in such a way that together they recover how things interpolate in the continuum, but not all the infinite dimensional details, but suitable topological information. But that's the rough idea. Right. So now let's see, what if we do the previous things and apply to more general cases, and what kind of problem we will encounter. And this part will include some mathematics. So we have seen two examples, right? So it turns out these two examples can be formulated in terms of both in terms of some fiber bundles. If you haven't seen what fiber bundle is, it doesn't really matter, because you know one certain thing. A circle is just R mod 2 pi z, right? That we know. A real number mod out the 2 pi times integer is a circle, just like a clock, right? The time is a real number, but we mod out the hour, then the minute live on circle, right? Yeah, so this notation just means the circle is R mod 2 pi z. And similarly, it turns out that the two-dimensional sphere S2 is a SU2 rotation mod out the U1. Yes, that's somehow maybe familiar from the spin, right? A spin has a direction on S2, but the SU2 is like the rotation of the spin, and the U1 is like some remaining Berry phase of the spin, right? And indeed, this U1, S2 is SU2 mod U1, and the U1 is interpreted as the Berry connection of the spin. And then again, this U1 is just R mod Z, right? And in this case, this R will correspond to the Berry curvature, and this Z will correspond to the Sturmian number. Okay, just like this R corresponds to the amount of traveling, and this Z corresponds to the winding number. Okay. And what does this modding out do? What does this picture do? It turns out there is some theorem in the mathematics that says if you do this thing, then the pi1, the one-dimensional winding number around the S1, will be captured isomorphically by the pi0 of the integer, which is how many components the integers have. That's why the V-line model can capture the winding number by viewing the S1 as R mod Z. Okay.
Because when you do the exact sequence, the first and the final, it's related, right?
Yeah. And similarly, this is how it works. The pi2 of the two-dimensional sphere through some mathematical theorem is captured isomorphically by pi1 of the U1 Berry connection. And then that's further captured by the pi0 of this V-line integer field. then it seems obvious what we should do for S3, right? For S3, we should just have a picture with one more layer. Indeed, let's consider S3 or SUN non-linear model. Okay, you can ignore the SUN here. Just think of this as a three-dimensional sphere, S3, because indeed SU2 is the same as S3. Okay, let's consider this S3 here. It seems like you need to do something like this, right? You need to do something mod something so that the pi 3 of S3 is captured by the pi 2 of that, and then that is also something mod U1. So the pi 2 of that is captured by the pi 1 of U1, which is an integer winding number, and then you do the relay so that the pi 1 of U1 captured by pi 0. It seems you can just do this and the problem is solved. But that's exactly why people could not solve the problem before. First of all, in the past, people didn't think about it in terms of this picture. But once they think about it in terms of this picture, they will know this would not work. Why this would not work? First of all, we can even know what the physical meaning of these things are. It turns out that these things will be related to Western-Minot-Witten. If this is non-linear model, or if this is Yang-Mills gauge theory, this will be related to Chen-Simons and instanton. Okay, those things even have a very good physical meaning that we know on the lattice. But the problem is, it looks like all we need is to fill out the question marks. But if people really thought about it this way, they will very quickly realize you cannot fill out a question mark. Why is that? Because there is a simple reason that this question mark is a link variable. Because this is a vertex variable. Because this is lives on the lattice vertex in a non-linear model that lives on link. Let's look at the previous slide. Like in the relay model, this is S1 is the vertex variable, but these are the link variables, right? And here, the S2 is the vertex variable. These are the link variable. These are the plaquette variable. Okay. So in this picture, this is a vertex variable, and this is a link variable. And that's a plaquette variable, and that's the cube variable. So the link variable, when we consider two links being joined to each other, then it seems like we also want the variable to be able to compose, right? If we go along this link and along this link, it seems like we want some group element on the link so that we can have this group element multiplied by this group element, right? So because this is a link variable, so it seems like we want this variable to be able to compose. So traditionally, we will think about some groups, okay? But the problem is the finite dimensional Lie groups always have trivial pi 2. That means it cannot complete this mission because the mission you want it to serve is it capture the pi 3 of S3, which is the integer winding number to here, right? So you want this thing to have integer winding number and then transmit the integer winding number here and to here. But this, now we see that there's a very general mathematical theorem. Any finite dimensional group does not have pi 2. So it cannot serve this mission. That's why people have tried different ideas for many decades, but didn't work. Because if they put the thing in this kind of picture, they will immediately realize that it will not work if you work with the traditional mathematics. Moreover, these pictures actually correspond to fiber bundles, and it can show that fiber bundles in general would not work. I'm not going to talk about the details.
Sorry, so is the theorem that in any finite Lie group, pi 2 or higher will be 0?
No, only pi 2 will be trivial, right? But they all have pi 3 except for U1. Yeah.
Okay. How can I think of it intuitively?
It's not very easy to prove. But roughly speaking, you can sort of imagine that all the Lie groups at least contain SU2, except for U1. Except for U1, all the Lie groups at least contain SU2. Okay. And the SU2 doesn't have pi 2 because it's a three-dimensional sphere. And somehow they contain SU2 in such a way that it's not introducing, yeah. Okay. So something like that, yeah. It turns out that not only cannot this be a group. Moreover, it turns out this picture, when you draw it like this, which means a fiber bundle in mathematics, it doesn't work at all. I'm not going to explain why, but you cannot work with it. So in the end, what we will need is some new idea, more flexible mathematical structure. And it turns out the mathematical structure has such a feature. The degrees of freedom can be composed somewhat like a group, but their composition is not the same as a group. For a group, the composition is unique, right? You compose something and something, you get some unique result. You need some more flexible composition that when you compose two things, you get some result, but the result is non-unique, okay? When you compose two things, you get multiple possible results. And moreover, you can talk about the relation between the different results, okay? It's like here, G and F can compose to H. But G and F can also compose to H prime, another possible result. And the composition may be via different procedure. G and F can compose via the procedure called psi to some result H. But G and F can also be composed via some other procedure psi prime and get some other result H prime. But you can also talk about the relation phi between H and H prime. So it's a more flexible structure than groups, right? For groups, it's like G and F has only one possible composition procedure, and the result is unique. And moreover, it's associative and so on. So you need some more flexible mathematical structure than group. And this all comes from very real physical problem, right? The real physical problem is we want to define proton and neutron in the pion non-linear model for the instanton in Yang-Mills theories. Completely physical problem, right? Motivated by completely physical problem, so through this very regular discussion, it turns out that we need a very unfamiliar mathematics just for this very physical problem. So it's not like I want to do some fancy mathematics, very abstract mathematics, not because of that. It's I start with a very physical problem and it requires the general mathematics. And it turns out that the mathematics is much like a board game where you have already, for example, you have already built some roads and some wood supply and some river or something. And then in the board game, the next step, you can ask which type of castle can you place in the board, on the board, okay? It's very much like board game. And this is not, I'm not trying to be funny by saying this. This is literally, almost literally what the mathematics is, okay? And then with this mathematics, I can talk, we can have some explicit main construction, which I don't have time to go into, but the main construction really is this kind of idea. Okay, you have built some, you can see that there's no fancy mathematics here, right? Even though it's deep mathematics, but it's not like any group, like you can compose a row and a wood supply and then you get something. You don't talk about you can get something, right? You just talk about you have already built this previous structure. What new structure can you build on top of that? That's actually the very flexible mathematics. It's not like a group where you have this compute with that, get that, right? And moreover, the computer can understand this because you can imagine a computer can play a board game, right? Then if a computer can play a board game, we can also do the Monte-Carlo with this kind of mathematical structure, okay? So with this, you can have a detailed construction, which I'm not going to go into, but as you can see, it has a very geometrical interpretation at every step, just like the previous Villain model and spin-on decomposition. It has a very geometrical interpretation, and also for gauge theory. But let me just briefly sketch a systematic relation between lattice QFT and continuum QFT. And it's actually related to famous mathematician Grothendieck's dream in homotopy theory in math. So that's very exciting that you start with some very physical problem, very physical motivation, and that naturally leads you to the history of the development of some very formal mathematics. Previously, we have already seen this slide that we want the traditional field and some new fields together to recover the desired interpolation information in the continuum. And in the pi1 and pi2 examples on the lattice, whose result is known before, it turns out that this structure together forms some fiber bundles that we saw in some previous slides. But more generally, mathematically, it's impossible to use these previous ideas like group theory or fiber bundle to fulfill the goal. And we need more flexible rules of the board game. And more flexible rules are phrased in terms of higher categories. So the general idea is that these things should form a finite dimensional higher category to recover the information of the interpolation.
So basically, because of the problem of pi2
yes.
only, can we continue to this direction using group theory and upper using category?
I think it's the first step you need to category. The upper long.
Because the form is pi 3, right? I can.
Yeah. So some final step will involve group theory, but there are some intermediate steps that cannot use group theory, right? And the idea is this. So when we talk about a field in the continuum, we just mean just like this. It's a map from the space-time to some target manifold of the degree of freedom, right? So a field in a continuum is a map from the space-time manifold M to the target manifold T, just like this is a map from S1 to S1, or more generally is that. And what do we need on the lattice? Traditionally, what we have on the lattice is, okay, we have this map from the continuum to the target space, and this L0 means the lattice vertices. It's sampling some discrete points in the continuum, right? And because it's sampling some discrete points in the continuum, of course, a lot of information is lost because you didn't sample all points. You just sample some discrete points. Now, let's forget about the lattice for a moment. Just think about the continuum. In a continuum, we can think about this. We can think about the manifold, but we can also think about the space of all paths on the manifold, and the space of all paths between paths, which is our surface on the manifold, and a higher and higher dimension, consider d-dimensional volume on the manifold. And then, when we know how the points on the space-time map to the points in the target manifold, then we also know how a path in the space-time map to a path in the target manifold, because a path is made up of points. And similarly for surfaces and all the way up. So this really has no new information. It seems like I'm just making things more complicated but not achieving anything. But once you put the lattice perspective, it becomes useful. Because when you sample the lattice vertices, you lost some information. Now you not only sample lattice vertices, you sample lattice links. That lattice link can be viewed as some path embedded in the continuum. Then you retrieve more information, right? You retrieve more information. And you go up, you consider lattice plaquette, you retrieve further more information. And all the way up to d-dimensional lattice cells, then the d-dimensional lattice cell will completely fill up the continuum manifold. So you retrieve all the information. Then you haven't lost any information. You have exactly the same amount of information, the infinite dimensional information, as the continuum theory. So this is still the continuum theory. It's not a lattice theory, even though we talk about a lattice, but it has the same amount of information in the continuum theory. And how do we see that it's actually not a good lattice theory, but a continuum theory? It's because these spaces are infinite dimensional. For example, if you consider target space to be a sphere, for example, then the space of all paths on the sphere can take all kinds of shapes, right? So the space of paths on the sphere is infinite dimensional, right? So in general, all the higher dimensional path spaces on a target manifold are infinite dimensional. That's why it contains the same amount of information as in the continuum. For a lattice theory, we want things to be finite dimensional. So now this has become a well-defined mathematical problem. It turns out each column actually forms a higher category on its own, mathematically. And then you just want to construct some finite dimensional higher category such that in some suitable sense, it has the same amount of essential information as this infinite dimensional higher category. So that's the idea. The two categories are different, but there is a mathematical standard for saying when do they contain the same amount of essential information. So by doing so, all the topological information that we can detect will be captured by this finite dimensional structure.
So the price that you introduce a new field and basically
on all the levels, right?
And basically the way that you preserve information by doing the path integral of the new field. Right.
So the idea, right? So what we have achieved is following. Usually we say we want to put a continuum theory on the lattice. That's a very vague statement. But now this becomes a very well-defined mathematical problem, right? We can just give a particular problem to the mathematician and ask them to solve the particular problem. So yeah, in summary, what we have done is in the continuum theory, we have a field configuration is very simple. It's just a function from the space-time to the target manifold, to the target space. Yes.
Sorry, I have two questions. First is at each level, when you go from L0 to L1 to L2 and so on, at each level, do you have to introduce a new field?
Right. This is a field. This is a traditional field on the vertex. That's a new field on the link. That's a new field on the pocket. So in general,
At each level, you have to.
In general, yes, but in specific cases, maybe not. Yeah,
Okay.
but in general, yes.
And then secondly, in the previous slide, you said that you showed that this is an infinite dimensional space.
Right.
And then,
These are infinite dimensional.
Yes. So what is this precise mathematical problem that you're posing to
the mathematical problem is that this is a higher category. Because you can see that the path and the points are not independent, right? Each path has a starting point and ending point. And also each surface has is interpolated between two paths, right?
Okay.
So this actually has some structure in between. Okay. So this forms a higher category. And the mathematical problem is you want to find another higher category, but finite dimensional in each layer and continuous mapping everywhere, such that the lowest traditional degree of freedom is the same as before, but all the higher dimensional degrees of freedom become finite dimensional. However, as a category, this category and that category are equivalent up to what we care.
Okay, so there will be some operator or something which.
There will be some statement in category theory say what do you mean when that they are equivalent up to what you care. Yes. So in summary, what we have achieved is a field configuration that looks like a very simple function in the continuum, but the problem is this infinite dimensional configuration space. On the lattice, it expanded to such a structure which seems very complicated, but the configuration space can be made finite dimensional. So this is the trade-off, but this is a very systematic trade-off.
And in the kind of I2, S2, you only need to consider
the two layers. Yeah.
And in this case, you need to consider the very connection on the link, but you don't need to introduce.
There's also a line, integer flux, like the Dirac string on the.
So basically, the very curvature you also need to introduce.
Yeah. Basically, if you need to capture pi n, then you need n layers. Here, yes.
No, I mean. You say that some layer you don't need to introduce a new field.
If when you care about pi n, you need n layers of fields.
But that should
So the trade-off is in the continuum of field seems very simple, but the possible fields from an infinite dimensional space. On the lattice, a field seems very complicated mathematical structure, but you can make it finite dimensional configuration space. That's a very systematic and beautiful trade-off. So in the end, you get something like this, from the lattice to some finite dimensional category.
What is the example when you don't need to introduce a new field called?
Maybe we can talk about that afterwards, because I'm already over time. And then actually this development of the ideas completely motivated by the lattice theory, right? We're motivated by reviewing what happened in the Villain model and the spin non-decomposition, which are known before. We just reviewed those examples and extracted these ideas. And it turns out that this motivation from the lattice physics resonates almost the same as the development of homotopy theory itself in mathematics. So that means we are doing something very natural, both physically and mathematically. So this is a very nice resonance. For gauge theory, there is something similar. So that is the ultimate picture, and so the outlook is that we want to use this idea that relates very formal mathematics, but also have very intuitive understanding, and it's actually useful for real physics problem in both high energy physics and condensed matter. And also with these categorical ideas, probably I want to also discuss like understand renormalization more systematically and so on and so forth. Okay, that concludes my talk. Thank you.
Thank you, Jing-Yuan, for this explanation. We have time for this.
when you are saying that you want to understand actual lattice model,
Yes.
say in, but as far as I understand, so you have a continuum model,
Yes,
and then you can put it on a particular lattice.
yes,
And then from the continuum model, you already know the topological operator that you
yeah.
are sort of
You
expecting.
expect, yes, yeah.
And then you can modify your lattice theory to
Yeah.
include this.
Right.
This,
Right, that's the
topological-
idea, yes.
Right. But so then I guess the more important question is just that which continuum theory is correct.
Well, depending on which system you are interested in. For example, we know QCD is certainly a correct theory of nuclear physics.
Okay, continuum one.
Yes, as a continuum one. And then we can people have already put it on a lattice and reproduce a lot of experimental results. For example, the mass of proton is that value and so on. So they can, so they know the lattice QCD also agrees with the experiment.
Okay.
And also the continuum QCD is also the correct theory. But like in the lattice QCD, there is some part of the continuum QCD where the question they cannot ask. The instanton effect should be there, but because the instanton is not well defined on the lattice, then they cannot ask questions related to instanton. For example, if you have some instanton density here, how does it affect the nuclear behavior nearby? That kind of correlation they cannot ask because the instanton is not well defined. Now with this refinement, you can ask those questions and explore those questions, yes.
And do you also now anticipate if I put these, like if I choose a different lattice, or like as previously was asked,
Right.
if you now have different sort of boundary conditions, like
Right.
state boundary conditions or something.
Right.
So in that case, do you anticipate having the same topological operators, or it will?
Yes, I expect that. But if I can prove that, then I already got the Millennium Prize. So I cannot prove that because that's related to whether lattice theory converges, regardless of lattice detail, right? So if I can prove that, that's like the Millennium Prize problem. One way to prove the Millennium Prize problem. But I cannot prove that, but numerically you can check that. And for example, in lattice QCD, you can make the lattice size smaller and smaller, and it seems to converge.
So with each lattice, mathematicians have to go and find all these levels, like the T's that you wrote.
Right. Mathematicians are currently struggling with the convergence. Yeah. So, but now numerically we can check whether it converges well. Yeah.
Numerically, what converges?
Like when you make the lattice size smaller and smaller, whether it converges, right? But in principle, you can also ask like different shape of lattice and so on. Yeah.
No, but you have to find spaces, like, so I don't understand what.
Oh, you mean those T1, T2,
Yeah.
that category thing. Oh, that is the same. That is the same.
Okay.
That is essentially the same for different lattices. Yeah.
That is essentially same for different.
Yes.
And you said that if you do if people do the usual way, they do not capture the topological operator. But what happened? Like let's make some kind of like physical interpretation. If you have a system with open boundary,
yeah,
I can expect that the voltage can move from the boundary to here naturally. Doesn't need to be the inside.
Yeah.
In this case, you can have a system with the number of voltage is not the same.
Yeah, but then you have the winding number on the boundary.
But
winding number is also not well defined.
Not well defined, but I can simulate a system with many like
very small lattice.
Yeah.
Yeah. So that's what I said before. You can, for example, in the V-line model, the V-line model, the XY model without the new field can have the exactly the same predictions as the V-line model and the XY model can have the same prediction if you make this a strict equal sign here. Right, because the V-line model summing out M, you can recover the XY model.
But my point is that when I simulate a system
with just the XY model.
With just XY model,
right?
With open boundary conditions.
Yeah, then you cannot define the vortex properly, even though the vortex effect is still there, because in the V-line model, you know you can both define the vortex and the vortex is actually there. And after summing over M, the vortex effect certainly is still there because it's same theory. But you cannot define the vortex observable anymore because the related degree of freedom is already summed over.
But at least I can see the BKT transition.
You can still see the BKT transition, but you cannot ask some relevant question, like whether the BKT transition you get from the numerics is really related to the vortex. That is very hard to answer if you study the XY model. You still can, but it's not very natural. But with the relay model, because the vortex is well-defined, then you can ask a very well-defined problem of how does the vortex affect the BKT?
If I do the particle vortex duality and study this side,
right?
And I can still
right. With the relay model, if you choose this to be Gaussians, if you choose these peaks to be Gaussians for simplicity, then with the relay model you can derive the particle vortex duality explicitly. But with the XY model, you cannot do that. And to derive the particle vortex duality explicitly, you need to be able to describe the vortex explicitly. That's why you can only do it with the V-line, but not in the XY. It's not related to whether the XY is Gaussian or not. It's not related to the Gaussian or not. It's the key is in the V-line model, the vortex is explicitly definable so that you can explicitly derive the particle vortex duality.
But at least in the effective theory level,
you can write.
Yeah.
You can write down the.
Yeah.
You can claim.
Yeah,
yes. Yes, but with it you can explicitly derive.
In this effective theory, I can study the physics of the vortex using the particle vortex duality with some source grain apply qualitatively.
Yeah. Yeah, but I am just saying in general, for example, in very strongly correlated systems, you need numerics usually. Yeah. But in particular problems, maybe you can say something else.
Even I'm too naive because it may work for this I1, but maybe for this I3, this thing doesn't.
Yeah, maybe you cannot do anything analytical in general if it's strongly coupled. Yes.
Okay, so last question.
So this is I somehow understand that this is like you start with XY model and some topological invariant or operator.
Yes.
And you write a lattice version of that. I'm sure you are familiar with this topological phases of matter. So like 10-fold classification.
So
the
topological order.
Yeah.
Kind of physics.
So,
yeah.
Yeah. So I'm asking like.
Right. This is a very good question.
Yeah.
Yes.
But it's not the thing that.
Not. Yeah, I know. Yeah. So let me comment on this. So this is right. So what you are asking is like topological quantum field theory, where you only care about the topological things, not anything dynamical.
No, I mean, what he asked is that the 10-fold way thing that.
The 10-fold way. Yeah, that's related. This is some symmetry part of the. Yeah. You can also include symmetry in. Yeah, like the 10-fold way is part of the symmetry and topological stuff. All those things. Basically, you only care about the deep IR limit because you only care about phase of matter. You don't care about any detailed dynamics. The motivation here is you care about the UV or some intermediate energy scale, not just the IR limit, because the IR limit of the physics is like the phase of matter, right? So of course we care about the phase of matter, but in general we want to care about more about just the phase of matter.
I think that's what you mean that you want to ask about relation.
Yeah. So first of all, they are asking. They are different. They have different interests.
I think what he has in mind that's a 10-fold way when you use a band theory.
Yes.
The band theory classification.
Yeah. So the classification is only cares about the phase of matter, right? Based on symmetry. But here we are asking about general energy scale physics.
So what I'm curious, like in that classification also we use some notion of topological invariant, right?
Yes.
Topological operator.
Yes.
So that had also the same problem as here.
No, not the same.
Not quite the same. Not quite the same. Yeah.
Because
These are real space topological configurations, for example. Yeah, those are, yeah.
But you can also define the real space topological operator in the topological phases, right?
Yes. Are you asking about tenfold way kind of things? Yeah, so those are associated with certain symmetries, like the PCT symmetries. So those are different aspects. They have some similar aspects of topology, but the problem you face are different, both physically and mathematically.
Okay, so tenfold just classifies the matrix.
Yeah. So the mathematical challenge is different, and also the physical motivation is different. For example, this topological operator may be important in the IR, but also they may be important in some intermediate energy scale.
Okay, and with that, we conclude our seminar. Let us thank Jing-Yuan for this excellent presentation again.